exponential functions and the natural exponential function e to the x. And we're going to work with any exponential function or things of the form y equals b to the power x. Y equals b to the power x with a couple extra conditions. Number one, b is always greater than 0, and we're not going to make b equal to 1. b greater than 0, b not equal to 1. Why not equal to 1? Well, because then you're just going to have 1 to the power x all the time. You're just going to wind up with a graph that is a horizontal line. So we're looking for exponential functions which show either exponential growth, which you probably remember from a curve shaped like that, and exponential decay, which hopefully you remember from Algebra 2. There would be something of that type of nature. So in our class, we focused on a couple graphs, and I'm going to go over them just very, very quickly. Y equals 2 to the x, y equals, for our purposes, 3 to the x, y equals e to the x. Again, because of the fact that we have limited graph paper, so on and so forth, and exponential functions get very, very big, very, very quickly, typically we're just going to focus with values such as 2, 3 from an integer standpoint, and e, which if you remember from your good old calculator, you can get to by doing nothing more than hitting the second button, then hitting your ln, which gives you e to a particular power. Then you can go ahead and enter whatever power. So for instance, if I want to do e cubed, I can do that and come up with a value of 20.08, some change. Always remembering that e to the first power is that special number. It's 2.718 and goes on forever and ever. But usually 2.7 is what we say e represents. It was used last year for continuous compounding of interest, for continuous growth. We also used it sometimes for continuous decay, when you maybe have a cell or something that's dissolving in water or something that is decaying. We used to have something e to a particular power representing how quickly something dissolved, how quickly something grew. In any case, there are a couple key pieces that we then did. We started to graph some of these functions, such as y equals 2 to the x, y equals 2 to the negative x. Then on subsequent pages, we had y equals 3 to the x, y equals e to the x. So here's what I'd like you to recall, and you might want to go off on your own and build just a very simple graph sheet. I've done y equals 2 to the x, y equals 3 to the x, y equals e to the x. Obviously, I have a very short amount of graphing scale here, but what I've done is I've created a little table. 2 to the negative 2 power is 1/4. 3 to the negative first is 1/3. 2 to the 0, 3 to the 0, always 1. And I built some very simple, what I call anchor points. And what I'd like you to make sure that you do is just go ahead and build yourself your own little parent graphs. Y equals 2 to the x, y equals 3 to the x, y equals e to the x. And by the way, with y equals e to the x, e to the 0 is 1. E to the first power is just good old e, which is about 2.7. E squared is about 7.4. You can see that graph. I'd like you to know these points, or at least be able to build it very quickly. You can use your calculator, obviously. So for instance, if I go into my y1, I'll just clear out what I have and do 2 up to the power x. Go ahead and do a quick table. I have all the values that I need to work my way through here and graph that very, very quickly. I can do the same with y equals e to the x, obviously, as well. But I'd like you to know these points because, or at least be able to understand them, because if you have these built, you can do some very, very quick transformations off of them. Now, as we talked about in our notes, exponential growth or exponential decay functions, a growth function is one in which the value of b, the number that we continue to multiply by itself, is greater than 1. We said that if we're between 0 and 1 with our base, our value that we keep multiplying by, we have an exponential decay. And there were a couple other key things we talked about. These are one-to-one functions. Going to be very important because as a one-to-one function, their inverses are going to be functions as well. The domain of every exponential function is going to be all real numbers. We always, no matter what the value of b is, 0, 1, the y-intercept is always going to be the same. It's always a point that you will have when you graph an exponential function. And for that matter, 1 comma b is also a point. With 2 to the x, 1 comma 2. With 3 to the x, the point is 1 comma 3. With e to the x, the point is 1 comma e, or 1 comma 2.7. The range of all these functions is 0 to infinity. You can see that again with all the different ones that we have graphed here. And also what's important with the exponential growth functions, we always have, and it's also true with an exponential decay function, we're always going to have a horizontal asymptote at y equals 0. So let's start talking some transformations. And there's one other important point I'd like you to get off to your side here, and that is any vertical shift. When I transform any exponential function, any vertical shift is going to move the horizontal asymptote. Any vertical shift will move the horizontal asymptote. So let's start looking at a couple of the problems that we had. First one said, hey, can you go ahead and graph y equals 2 to the x? Well, no problem. We already had done that. We said what? Remember, 0, 1, 1, 2, 2, 4, and 3, 8. And again, we could have gotten this straight from the calculator through a table, but here comes 2, 4. And go up 1, 2, 3, 4. There's 3, 8. I know I get to 1/2, 1/4, so on and so forth as I keep moving along. And what do I have? I have my good old horizontal asymptote here at y equals 0. Now, 1/2 to the x is the same as 2 to the negative x, which is nothing more than, look, that negative x is living where? I do that before I take 2 to the power. That's a horizontal impact. It's a horizontal flip over the y-axis. So what I can do very quickly is I can take each of these points that I see and just flip them horizontally. Hey, 0, 1. Hey, when I flip 0 over the y-axis, it stays at 0. My point that was 1, 2, gee whiz, all I got to do is change my x-coordinate. It now becomes negative. I flip over the x-axis. I have the point -1, 2. The point that I used to have at 2, 4, the point I had at 2, 4 is now going to become -2, 4. There's -2, 1, 2, 3, 4. My point that happened to live at what? Way up here, 3, 8 now becomes, flip it, -3, 8. My point that was at -1, 1/2 now becomes 1, 1/2. My point was at -2, 1/4 becomes +2. All I'm doing is I'm making my x-coordinate. It used to be positive, now it becomes negative. Where it happened to be negative, now it becomes positive. And there's my good old exponential decay curve running along again, a horizontal asymptote at y equals 0, coming from way above. Notice one other thing. Hey, domain stayed the same, all real numbers, and so did the range for that matter, 0 to infinity. So let's look at some problems that are a little bit more complicated or have a little bit more structure to them. Y equals 3 to the x, y equals 3 to the power x minus 1 plus 2. Well, I've already gone and drawn my parent function one more time. I've used my nice little table here, -2, 1/9, -1, 1/3, 0, 1, 1, 3, 2, 9. I'll kind of keep that tucked here up into the corner. And what do I know? Hey, in this transformation, 3 to the x minus 1, that x minus 1 is living in the exponent. Before I go ahead and take 3 to a power, I have to figure out what the power is. This is a before operator. This is a horizontal impact. Since it's -1, right 1. And then plus 2, that's after I do 3 to whatever power. That's a vertical impact, and it's an up or down. In this case, it's up 2. So the first thing that comes out that's very, very useful, remember we said horizontal asymptote travels with any vertical shift. Well, my horizontal asymptote used to live at x equals 0, at y equals 0. Now it's going to live at y equals 2. So I'm already going to go ahead and just start my dashing. And then all it's a matter is, hey, I can take these points and do what the transformation said. Hey, take it right 1 and up 2. So gee whiz, 0, 1 becomes now right to 1. It's going to become a 1. It used to be a y-coordinate of 1. When you raise it 2, it goes to 1, 3. I have a point identified. Go ahead and mark out my whole asymptote here just as I go at y equals 2. What do I also know? 1, 3 becomes, move it over 1. X-coordinate goes from 1 to 2. y-coordinate up to 5. 2, 5 is my new point. 1, 2, 1, 2, 3, 4, 5. And with that same type of logic, 2, 9 becomes 3, add 1 to the x-coordinate, go up 2, add 2 to the y-coordinate, 3, 11. 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And what else do I know? My asymptote is moved. And where do I come from? Well, I just come from that asymptote down here. So there is my transformed graph. Y equals 3 to the power x minus 1 plus 2. All right, we already talked about e to the x here. Remember, it's just another exponential function. It carries all those same things that our other functions, y equals 2 to the x, y equals 3 to the x, have carried. Let's do some work now. We're going to save this last example just so we'll have a little bit more leg space to work with. But let's talk about this graphing practice problem, y equals 2 to the power x plus 2 minus 1. Well, if we think about it, it's going to work off of a parent of y equals 2 to the x. So let me put my points out there again. Remember, 0, 1, it's always a freebie. Here comes 1, 2. Here comes 2, 4. There comes 3, 8. And I know I got my asymptote running along this way, and I'll go ahead and dot it in blue. I'm going to switch to a red pen, and let's talk about our transformations. 2 to the x plus 2, left 2, down 1. Well, first things first, it's a down 1. What do I need to do with my horizontal asymptote? Move it down 1. I'm going to have a horizontal asymptote living at x equals negative 1. Great. Now, I can start transforming points. And again, I always like to work with the integer points. So I'm going to move left 2, down 1. 0, 1, when I move left 2, that goes to negative 2. When I move down 1, the 1 becomes a 0. The new point is negative 2, 0. Let's keep working. If I'm at x equals, my coordinate point is 1, 2. If I move 2 to the left, my 1 becomes a negative 1. If I move down 1, this becomes a 1. I have another point. So negative 2, 0 is a point. Negative 1, 1 is a point. 2, 4, move left 2, that becomes 0. Move down 1, this becomes 3. 0, 1, 2, 3. And finally, my 3, 8 is going to become a 1, comma 7. Left 2, down 3. Excuse me, left 2, down 1. I could also have just worked off these points, right? So watch me do it this time. Left 2, down 1. Where did I wind up at? At 1, 7. Again, my asymptote is a little bit lower this time. So I will ride off towards my asymptote. This is a growth function. So I'm working towards negative 1. And then I just go ahead and draw the rest of my curve. It keeps its shape. And we're good to go. By the way, my fault here, just on my parent, I had forgotten to extend with an arrow as well. Let me just clean that up. If I was asked for the domain of this transform function, just like everything else, negative infinity, positive infinity. And if I'm asked for the range, well, the parent's range used to be 0 to infinity. Now, with the horizontal asymptote having moved down 1, the new range becomes negative 1 to infinity. Okay, let's do another function. We're going to do our bottom problem, e to the negative x plus 2. And we'll work off everything we know about the function y equals e to the x. Let me fold a sheet here. And had a little bit of a problem here with my graph having gotten truncated. So here's what I'm going to do. I'm going to go ahead and right there in red, scroll down just a little bit, that's where I'm going to put my bottom. That's where the x-axis will live. That's the line, and it'll be also, for the parent, the horizontal asymptote. That is y equals 0. So if I do e to the x plus 2, which would be the parent function, well, I'm going to go ahead and build it again. Using my table up here, 0, 1, 1, 2.7, and then 2, about 7.5. 2, 1, 2, 3, 4, 5, 6, 7 and a half. And I know that I run off towards this asymptote. So there's pretty much what a parent would look like. I'll go to blue and work on my transforms. And again, let's work with the easiest pieces. What do I have this time? I have e to the negative x plus 2. Well, I know one thing. I'm going to be a vertical shift up 2 and e to the negative x. That is a horizontal flip over the y-axis. Okay, so what will I work with as I work through a problem like this? I'm going to use the table. First things first, I know what? Gee whiz, everybody goes up by 2. And what else do I know? Every point is going to what? Flip over the x-axis. I know my shape is going to be something like what I draw right there. Just kind of watch my hand. Let's go ahead and start to build. And again, we'll work with kind of the points that are easy to see. 0, 1. Well, when I flip 0, 1, my x-coordinate doesn't change. When you flip and you're already on the y-axis, you stay on the y-axis. But I need to move up 2. That point will now become 0, 3. So 0, 1 becomes 0, 3 in this particular circumstance. My next 1 is the coordinate. So the original point was 1 and 2.7. Well, now what am I going to do? That's going to become negative 1. That's my flip. And what happens to my y value? It goes up by 2. It used to be 2.7. 2.7 plus 2 is 4.7. So there I go. I'm going to move over. There's my flip. I went from 1 to negative 1 as the x-coordinate, and then I'm going to move up 2 with my y-coordinate. Bing, bing. And there I am. And finally, what can I do next? Well, this point was 2 and about 7.5. Well, the 2 used to be positive for the x-coordinate. Now I got to flip. That becomes negative 2. And what do I need to do? I also need to add 2. So my 7.4 now becomes a 9.4. So I flipped, and then I'm going to go up 2. 1, 2, and I'll wind up somewhere about here. And when all is said and done, here's the rest. There's my arrows. And I'm going to ride towards that horizontal asymptote. This is an exponential decay type of problem. Domain, all real numbers. Range, 2 to infinity. So one more problem to handle very, very quickly, and that's the one up top here. It's also a e to the x as a parent, but I have 3 transformations this time. I have a minus 2 that I see inside the exponent. That's going to take me right 2. I see a plus 1. That's going to take me up 1. And now I have a negative e in front of the exponent. I'm going to change the sign after I compute e to the x minus 2 power. This is an after impact, and that becomes a vertical flip over the x-axis. Now, very quickly, what we're going to use this time is we're going to use our existing tables. I'm just going to go ahead and fold things here. And I'll have our table off to the side just a little bit. I'm going to scratch out these points that we used to have for the last example we did, but just use this table one more time. And I'm just going to talk about our transform locations. One thing I know, up 1, I already know where my asymptote is going to lie. Let me go in red here as I do this. I'm going to have my horizontal asymptote at y equals 1. Now, I'm going to build some points. I'm going to go with 0, 1. I need to go right 2. So 0, 1, I'm going to write this way, is going to become, well, I move right 2. That will become positive 2. Move right 2, positive 2. And then what do I have to do with my y-coordinate? Well, 2 things. First things first, make it negative. Well, it used to be 1. Now it's going to be negative 1. It used to be 1. Now make it negative 1. And add 1. Negative 1 plus 1 is 0. I have a point at 2, 0. let's keep rolling. When I have the point 1 comma e, or 1, 2.7, okay, I'm going to go right 2. That's going to become 3. What am I going to have next? Well, I need to take my y-coordinate, make it negative. Used to be positive 2.7, now it's negative 1.7. I'm going to go ahead and add 1. I'm at negative 1.7. Let's go ahead and take a look at what we'll have next. 3, negative 1.7. And let's do one more point. I used to be at 2, 7.4. What's going to happen now? Well, move right 2. That's going to put me at 4. And I need to flip my y value, which used to be 7.4. It's going to become negative 7.4. And what can I do then? Add 1. Negative 6.4. Let me go find it. 1, 2, 3, 4. Move down 6. 1, 2, 3, 4, 5, 6. Plus a little bit more. There I go. And so my new graph is going to look something of this nature. I could have also worked with the point negative 1, 1 over e, which was what, negative 1, 0.4. Let's work with that point just one more time, just so we can see where it comes out to. That's going to turn into, well, my negative 1 when I move over 2 is going to become a value of 1. My 0.4, I have to make it negative, and then add 1. That's going to give me a value of negative 0.4 plus 1, or about 0.6. And you can see here on the graph, it's about what I have drawn as I was working my curve through. So you can see 4 new points. You can see the shape of the graph. Domain remains all real numbers. What happens to the range? Hey, a little bit different. Before, we always seen the vertical asymptote as our lower floor. Now, because of this vertical flip, it's actually our upper boundary. The range of this function is negative infinity to 1. So again, the key thing here, be good at understanding where your original parent lies. Know some of these points. Remember, 0, 1, it's always a freebie. 1, b, whether it's 1e, 1, 2, 1, comma 3, those are always kind of freebie points or whatever. But if you know those points and then you can just walk through, hey, what do those points turn into? You have a very quick and nice way to go ahead and build these transform functions. Right, one more quick thing to just talk about is our back page here, which is where we're going to start solving exponential equations. We can do a lot of this with calculator, obviously, but for the purposes of what we're going to do, we're going to use some basic structures here. We're going to work off the bottom line property that you see here. If you have two bases that are identical, the same base, and you're raising them to at least variables that express powers, if b to the m equals b to the n, you know the exponents have to be equal to each other. And so we're going to see a lot of expressions of this nature where perhaps we might be able to convert something that's not quite like this at face value into something that is, and use this uniqueness property. It's right in front of us on our first one. 3 to the x plus 4 equals 3 to the 6th. Same base, 3 and 3. X plus 4 better equals 6, which gives us, when all is said and done, x equals 2. When you look at a problem like this, 5 cubed equals 25 to the x, you don't see the same base. But if you're familiar with some exponents as well, you'll know that 25 is equal to 5 to the 2nd power. That allows us to rewrite this as 5 cubed equals 5 squared. Notice I put parentheses around to show that it's 25 to the x power. When you raise something to a power to another power, you multiply the exponents. This tells me that 5 cubed equals 5 to the power 2x. It gives me, now I have the uniqueness property that I can use. I'm going to have 3 equals 2 to the x. 3 equals 2x. Again, same base, powers have to be equal to 3 equals 2x, or x equals 3/2. Next problem, very, very similar. Take a look at your numbers. Look for common bases. Start with the smallest number. Hey, can I write 81 as 3 to a power? Well, it turns out you absolutely can. 3 to the 2x minus 1. 81 is the same as 3 to the 4th power. So, what do I have this time? Hey, same basis now because I changed 81. I rewrote it as 3 to a power. 2x minus 1 equals 4. 2x equals 5. X equals 5/2. And our final problem, 1/3. Remember, we're always talking about our bases being integers or positive numbers. Well, we can work with 1/3 as well, but let's think about it in the context of an integer and also the 9. So we wouldn't write 1/3 as 9 to a power, but what do we notice? Well, I could write 9 as 3 squared. 1/3 I could write as 3 to the negative first power. I can turn them both into common bases. So let's do so. 1/3, 3 to the negative first to the 2x power equals 3 squared to the x minus 6 power. Power to a power, multiply them. -1 times 2x, that tells me 3 to the negative 2x equals, again, power to a power. Remember, this is a whole power. It's not the x and then subtract 6 after you multiply by 2. You got to multiply 2 by the whole thing. So 2 times x minus 6, notice how I've done it here, is the same as 2x minus 12. 3 to the negative 2x equals 3 to the 2x minus 12. Negative 2x equals 2x minus 12. Now, I'll just subtract on each side. Negative 4x equals negative 12. I'm not a big fan of negative something equal negative something else, but I can live with that. Divide both sides by negative 4. Negative 12 over negative 4 is equal to x equals 3. And there I am solved. So, in our first level of solving exponential equations, what can we do? Well, hey, again, we could put all these things into our calculator, but man, those graphs could get real ugly real quick. Instead, use this property, use some algebra, use all the things we know about properties of exponents, let them help us. Establish same basis for the values that you're given. If you can do that, you are much closer to a solution because now you can set your exponents equal to each other, just like we did in each of these problems. Varying degrees of difficulty with each of these, but what did we get to in the end each time? We got to exponent value equal exponent value. We can solve for x, we can solve these equations. So that's our intro to exponential equations. Hope this helps.